Okay, for example 7.6, the double star matching. Consider now the loading is 30 minus 40J. After the normalization is equals to 0.6 minus J.8. That's the impedance, normalized impedance. And for the double star matching, we adopt the conventional double star matching design, that is the D1 equals to 0, which means the first stop is directly connected to the position of the termination. And D12 equals to 0.375, so that it equals to 3/8 of a wavelength, and which is equivalent to 270 degree rotation on the Smith chart. So the first step is to locate the impedance of point A, that is 0.6 minus J.8, and you can once you found the location of point A, you can draw a constant SWR circle that goes through point A. And for double star matching and single star matching procedures, it's more convenient to work with the admittance. Why? So we can, how to do that? Well, to find out the admittance of point A, you simply rotate along the constant SWR circle by half a circle. So it happens to be the YR, the admittance of the load, happens to be on the opposite of the point A on the constant SWR circle. So the new point, which is in the opposite of point A, is referred as point B. So you can read the admittance of point. You can read the admittance of the load, that is YR, according to the real and imaginary par values that goes through point B, and it happens to be 0.6 plus J.8. So point B is which is on the opposite of point A, is the admittance of point B. So what the third step is to find out the susceptance required to move point B to the auxiliary circle. So according to the plot, you see there are two solutions possible for point B. You can move point B along this dashed line. What is the significance of the dashed line? This dashed line is the constant susceptance circle. 我讲错了 constant conductance circle. I'm sorry. This dashed line is constant conductance circle, and the conductance value is what? 0.6. So this circle, which is a full circle, equals to conductance of 0.6, and it's comprised susceptance of different value. For example, at point B, the susceptance is point A. And at the intersection of the point C conductance with the auxiliary circle is point C, and its corresponding susceptance is minus 0.09. Therefore, the required susceptance to move B to C is what? Minus 0.09 minus 0.8, so it's minus 0.89, 0.89，负0.89你要加上一个负的电纳值，才能够把 B 点转到 C 点注意这个旋转，它不是传输线的所造成的移动，它是在同一个位置上面，因为接上那一个 single stop 之后，让它的透过这样的并联，让它的等效导纳看到的有效的导纳值的虚部发生改变，实部没有改变，虚部有改变，所以它会沿着 这一个虚线来去旋转。好，所以你在做 Smith chart 的操作的时候，请你搞清楚哦。哈，有的时候你是要沿着 SWR circle 转，沿着 constant SWR circle 转的话，你是在传输线上面左右移动。但有的时候你是直接跳过去，哦，那是一个 Z 对 R 或 R 对 Z 的转换。那有的时候你是沿着 constant conductance circle 在旋转，哦，那是因为你并联让它的虚部改变。好，把这几件事情、这几个操作的动作分清楚，好，你在考试的时候才不会搞混。好，这边线在那边乱画，好，然后得多少分就只能看老师当天的心情如何嘛，对不对？好，何必把命运交到老师的手上呢？对不对？好，你要自己掌握。好 ，OK 好。好，所以 therefore the required susceptance is minus 0.89. So with this susceptance, you can move point B to C. You can also move point B to another intersection with the auxiliary circle. That is point C prime, right? And what is the susceptance of point C prime? It's minus 1.92. Therefore, the required susceptance will be the addition of the two numbers, the magnitude of the two numbers. So it's minus 2.72, I guess. Minus 2.72. All right. So that will be your first solution for the first stop. Now, the first stop takes minus J.89. And you have another choice. Well, I'll go a little bit further. So another choice is move the susceptance from positive point A to minus 1.92. Then the corresponding susceptance would be minus J 2.72. And an important technique pertinent to the single stop design and double step design, and also pertinent to today's Zuvio test, is how to find the short stop length according to the required susceptance. And what you need is a Smith chart, of course. And remember, for admittance, where is the position of the short on the Smith chart? Where is the position for the open on the Smith chart? For Y chart, for admittance, short, where is the short location? Right end or left end? I guess you're supposed to know that by now, right? Remember that by now, okay? I expect you to already remember this, okay? In the Z chart, short is on this side because the reflection coefficient is minus 1. And open is on this side because the reflection coefficient is positive 1. However, for admittance, the short position and open position will interchange, which will be swapped. So short in the Y chart, short position is actually on the right-hand side. Because the impedance of short is 0, so the inverse of 0 is infinity. So for the short termination with 0 length, its location is on the right-hand side. And if you extend the length of the short stop, the susceptance, the B value, goes to a large negative value. It still rotates on the clockwise. It still rotates clockwise. So it will start with infinity, then a very large negative value. Then the susceptance value will become, the magnitude will become smaller, or it become the magnitude becomes smaller. But it's a negative one. All right. So once you pass this point, its value is greater than -1. Now it's between 0 and -1. And once the length of the shortstop is greater than 0.25, a quarter wavelength, then you will have a positive susceptance. All right? So if the required value is minus 0.89 for this case, then it should be somewhere around here. You see here is 0.8. This point is -1. So you require minus 0.89 is about minus 0.9, all right, somewhere around here. So what is the length? Well, it's starting from this position and it goes to here, okay? So it will be a quarter wavelength for half circle. This is a quarter circle, so that will be 0.125. And so at this position, it's about 0.13 lambda for this shortstop. So let's check about the answer. 他其实没讲。Okay. So the first, so if you have the Smith chart at hand, you can find out the exact length required. So for L1, the first stop, which provides a negative susceptance of -J.89, the required length is 0.135. Okay, it's close to my estimation. So if we adopt this solution, point C, so you connect a shortstop in shunt at a position B, then it moves to point C. Then you shall follow the constant SWR circle and move clockwise. So you will move from the red circle to the blue circle. Then for the point C on the chart, with a three-quarter rotation, it will rotate to point D. Okay? So point D will locate on the uniconductance circle. And the susceptance read from point D is minus 0.53. So in order to move point D to the center so that you can achieve matching, the required susceptance is what? Positive 0.53. And what is the length of shortstops that can provide a susceptance of positive 0.53? Well, you're starting from the right end and you goes and goes and go. Probably it's 0.53, so it's probably somewhere on the second quadrant, right? So the length will be greater than 0.25, will be shorter than 0.375. Now, so I guess it's somewhere around 0.3, okay? 0.3 wavelengths. So let's check out the solution. Well, to provide a positive susceptance as 0.53, the shortstop, which begins from the right end, will have a revolution and a little bit more. So the actual susceptance required, the actual stop length, it will be 0.327. Okay? So that will be 0.327. And you can verify this solution using the Smith chart software. All right? I guess I will, yeah, if we have time, I can do that later. And let's check out the other solution. Let's check out the other solution. The other solution is for the double stop matching is moving from B to point C prime. OK， 那我建议同学还是上课的时候要听我讲啦，因为这一个动作就是你越做多次越熟练就越没问题了哈。只要你回去自己只看一次，然后可能作业只写一次，然后就考试就要。我跟你保证一定会乱掉，好不好？所以把握每次机会啦，尽量跟着我的说明Okay, the other solution is move point B to C prime. Okay, so we know that the susceptance begins with point A and ends up with minus 1.29. So the required susceptance is minus 2.72. So we know that a large negative susceptance value can be provided with a short stop, with a short stop of short length, okay? Because a shorted stop will provide a large negative susceptance, all right? So it's somewhere. So for minus 2.72, it's probably somewhere over here. So the length is about 0.06 wavelengths, I guess. So if you have your Smith chart at hand, you can check up with that to provide minus J 2.72. The required the length is 0.056 of our wavelengths. It's relatively small. And other stop at O2. So once you move to C prime, the next thing is rotates on the constant SWR circle with a 270 degree revolution. 270 degree. So you will move from point C on the oscillatory circle to point D prime. Okay, you can see here, D prime is on the constant uniconductance circle. The conductance is 1 and the susceptance is 3 as 2.5. 1 plus J 2.5 for position D prime. Therefore, to bring point D prime back to the center, what is the necessary susceptance required? Well, that will be minus 2.5, correct? Minus 2.5. So to provide a susceptance of minus 2.5, what is the length of your short stop? Well, still somewhere around here, right? It begins from here and it goes, once it moves clockwise, the susceptance magnitude becomes smaller and smaller, but it's negative 1. So to have minus 2.5, it's somewhere over here. Okay, so you can use your Smith chart to read the required susceptance. That would be to read the required length of your second stop. That would be 0.06. 0.06. If you draw the contour for this double stop matching design on the Smith chart, it turns out you enter the point at point 1 and move to constant conductance circle at the point 2. Then with susceptance, then you rotate 3/4 of a rotation to point 2. Point 2. Then you go back to, So this is the position of the oscillator circle, but you can you can see that, right? Because this is the Smith chart software tool, and it will go back to 0.4, that is the matching point. So, all right, let's try this with the with the Smith chart software. So let me write down the solution first. For the double star matching, the first solution is L1 equal to 135 lambda. Okay, so let's work on the Smith chart